Hello, good morning, good Monday morning. Hi, and welcome to another day of Advent of Code. Today is day 14 already. We are past halfway through the event with a total of 25 days. Before we go on with day 14, I'm going to do a recap of days 12 and 13, which I solved over the past weekend and I didn't stream. So I just want to go quickly through them and do the solutions that I came up with. Day 12 was about, so we were on a ferry onwards to our tropical island, and day 12 was about navigating the ferry. Your input was a list of instructions, which looked like this, and each instruction had a letter and a value. And the letter could be S, which stood for south, F for going forward, and then you had a W for west, and for north, and so forth. And then the value, that's the actual amount of steps that you had to go in that direction. So you had to calculate the answer for that puzzle input was to calculate the Manhattan distance of the destination where you would end up with. So the Manhattan distance is just the X and Y coordinate for wherever you are, the absolute values compared to the origin position where you started off, those two values added together. So for example, given this input, the ship would end up with 17 steps to the right in the X direction and 8 above in the Y direction. Added them together would be 25. So my answer was 441 given this input. The way I solved it was fairly straightforward. I just parsed the input into, split the input into an array of elements with each line being an element. And then I also made sure that I split out the instruction and the value. So I had the instructions and the value separate here, and then I went through each instruction, and then I just kind of like calculated the ship's position. I kept track of the X and Y coordinate and the current heading. So it was stated that the ship starting heading east, and therefore, like if you assume a compass, north is 360 degrees or 0, which is the same, and then east would be 90 degrees. So the current heading of the ship was 90 degrees, so I also kept track of that. And then as I went through each instruction, I just did whatever that instruction accounted for. So if it says north, then I just moved the ship up north with the value amount. But also if it said forward, forward means go forward in the direction you're currently facing. If it was forward and the heading was north, then it was the same thing basically as going north. So I did that for north, for south, east, and west, and then left and right would be turning the ship's heading. So that's what I did. I turned the heading with the value, which could be like 90 or 180 degrees, depending on whatever the input was. And then at the end, what I did is, if I would go, I would basically mod wrap around the 360s, because if I would be over the 360 degrees, say 450, then I would just, which is in here, then I said 450 minus 360 resulted in 90, which is the same thing. So I just kind of like wrapped it around, and I did that for in case the value was under below 0, then I wrapped it around the other way. So that's what I did, and then yeah, I computed the Manhattan distance here. It was pretty simple and fun as well. I love puzzles like these that involve grids and navigation. Hi Lars, glad to see you here again. Loyal fan, has been viewing my streams, I believe, every day for now, 14 days now in a row. So appreciate it a lot. Thank you for sticking around, Lars. Second part was a little bit more tricky. We found out that the actions were all relative to a waypoint. By the way, Lars, did you solve these weekend's puzzles? How were they? Difficult? Easy? So the second part was the relative to the waypoint. So you had a waypoint to keep track of, and then if you would say go the north, south, east, west values were for the waypoint. So the waypoint would be, say, you started off at 10 east, 1 north, means that if the instruction is go forward 5 times, then you would go forward to that endpoint 5 times. So it would go 5 times 10 east and 5 times 1 north. So you had to multiply the waypoint's coordinates times the times you're going forward. If you've been playing games, some of RPG games, I used to play Ragnarok Online back in the days, and it's an online RPG in a kind of like 3D map. If you're used to playing those games, they also function like that you kind of like hit a point on the map, and your character kind of travels there in a waypoint direction. And then if you keep it pressing, it just travels in the same amount of X and Y positions every time you go there. So it kind of like travels with each waypoint. So that was part 2. And rotating the left and right actions, we're not rotating the ship, but we're rotating the waypoint around your ship. So that was a bit more tricky, and you had to. So what I'm doing here, I'm using a JavaScript trick to swap variables. Instead of creating a temporary variable and assigning it to it, and I'm using a array destructuring to swap 2 variables, and rotating. So the logic here is, if you rotate something, let's start with this one, it's easiest. If you rotate the waypoint 180 degrees, that's basically just saying get the negative of the X and Y coordinate. So the new X coordinate is going to be the negative of X, because it's the other way around, kind of like mirrored. Same goes for Y. And then going 90 degrees on the right to the left is the same as going 270 degrees on the right, which is kind of like you're looping the other way around. So these two are the same. That's why left 270 is the same as right 90, and the other way around as well. And then just depending on whether it was left or right, you had to just mirror one variable. So like, for example, if you went left 90 degrees and you started at x10 and y is 1, then y would be 10, so y would be x in this case, like here, and x would be the minus of y, the mirrored of y, and the other way around here as well. So that was the rotation of the waypoint, which was a bit tricky to understand, but in the end the solution looks pretty glad with what I came up with. And then so the forward, as I was saying, if the ship moves forward towards the waypoint, it was just the waypoint x coordinate multiplied by the value and the y coordinate as well, and then you had the new ship's coordinates. So basically the same thing, keep track of the ship coordinates and the waypoint coordinates, and then compute the Manhattan distance here. So yeah, I managed to solve that about just over an hour, and was a fun puzzle, that one. I have a presentation tomorrow that I need to prepare. Oh, great. So you're still watching the stream, so appreciate that. Will you be solving them later on though, or are you gonna skip them and just go on with whatever day is today, 14? And day 13 was, the first part was okay. The second part was really brutal. And I'm gonna try and explain it, what it was about. First part, so you were about to arrive on the island, and you had to take a bus to the airport. And you had a bus schedule. The input was a bus schedule that looked something like this. And the first line was the earliest timestamp that you would arrive on the island. So the earliest timestamp you could take the bus. And then the second line was a bus schedule with bus IDs. The X's were buses not in service, so you could ignore those. And the bus IDs stood for how frequent the buses would go. So bus ID 7 means the bus went every 7 minutes. 13, it went every 13 minutes, and so on. So you had to calculate for the first part, you had to figure out, if you're arriving at minute 939, how long do you have to wait for the next following bus that will come to bring you to the airport out of all these buses in the schedule? So for this particular input, you would arrive at 9:39, and the next following bus would be bus 59, and which would arrive at 9:44. So you had to wait 5 minutes. And basically the answer was multiply the amount of minutes you had to wait times the bus ID. So here's 5 times 59 is 295. My input would look like something like this. So obviously it was much larger. This was the minute, earliest time you would arrive, and the bus schedule was larger. And the way I solved the first part was to grab the timestamp from the input, and also grab the buses in service. I would just split this string into an array with elements, with each bus ID being an element. So I would split it by a comma, and then I would filter out the x's, which I do here. Filter out the x's because we can ignore them, and then I just map those buses to numbers. So if we do, in case we do, when we do any additions, then we don't get any problems with adding strings in JavaScript. And then I just computed basically the waiting times for each bus ID, and I used the modulo operator to do that. So what I did is I said this is the earliest time that I would arrive on the island, and then this modulo 13 would give me a remainder, and the remainder is basically if you like if we go back to the example input here, if you do 939 modulo 7, you would get a remainder of 1, because that's how. So every time the bus comes, that's a whole integer that you can fit inside this timestamp. So 938 is the modulo 7 is 0, because 938 divided by 7 is an exact integer, is whatever that is. It's not really irrelevant, but let me just compute that. Can't I just? No. So 938 divided by 7 is 134, and that's exact. So when you do 939 modulo 7, it would be, okay, so 7 fits 134 times in 939, and then you get a remainder of 1, because that's like the 1 you need to add to come up with this to this number. And therefore, but I didn't need the remainder. I needed like this part, how many minutes I had to wait. So I just did the bus ID minus the remainder. So that gave me this, like this amount, which is the waiting time. So I computed that for each bus, and then I just basically used math min and JavaScript to get the lowest number given a set, so the shortest waiting time. And then I also had to grab the bus ID, because I needed to multiply the shortest waiting time with the bus ID. So the way I did that is just I had the shorter waiting time, so I found the index of that element in this array, and then I grabbed the bus ID using that index in here. So I found the index, and then I grabbed the bus ID using that index, because those two arrays were one-to-one mapped to each other, meaning the first bus in the service would have the first waiting times in the waiting times array. So that was part 1. Then the second part, as you can see here, a bunch of comments. I left a bunch of comments in the solution. This took me several hours to solve. It was really brutal. The second part was, the question was like this. So the timestamp was not relevant anymore. So this number was not relevant. You could ignore it. You had a bus. You had the same bus service list, but then instead of computing the shortest waiting time, you had to find out the first timestamp where each bus would come like in a congruent sequence. So given this input, you had to find out the first timestamp that when the first bus would arrive on the spot, like on that timestamp, and then the second bus would arrive at timestamp plus 1, and then you could ignore these, and then bus 59 would have to arrive at t plus 4 because it's the fourth bus in service in this array. So even though you could ignore x, you still had to take an account for, because it's kind of like spacing out the available buses. So, and bus 39 had to arrive at t plus 6 and bus 19 at t plus 7. So as the input gets longer, and with the input that we have here, the timestamp that the first timestamp which is valid for the criteria that we have here, that the buses need to go in a congruent scheme, becomes significantly higher. So as you can see here, with this small input, the timestamp which the first timestamp which the buses would go in like a sequence was 1,068,000. So you can see here, bus 7 comes on the spot, on the minute. Bus 13 comes a minute later. Bus 59 comes 4 minutes later. 31 6 minutes, and bus 19 7 minutes later. So that was the answer you had to solve given your input. And the puzzle already hinted that your answer was going to be larger than a 100 trillion. So a brute force was not, a brute force approach would not do it for this one. Meaning you could not go through each timestamp 1, 2, 3, 4, and so forth, and just find out if the buses go like in a sequence order. You have to use some clever math in here. So with a bunch of Googling and searching around, I found out about the Chinese remainder theorem. And if you're curious, I'm gonna drop a link to my solution in the chat, so you can have a look at the at all the links in here in the code. Geeks for Geeks is a very nice resource for algorithms and data structures, and here is where I got a really nice introduction about the Chinese remainder theorem. But it basically says, hey, given two arrays, one is an array of numbers, and two is an array of the remainders of those numbers, solve for x. And that's exactly our problem. Our problem is we have our first array of numbers is basically the bus IDs, and our second array is the remainders, which is the index of those positions of those bus IDs. So we need to solve for x. So here, this is our x, where the first number equals the remainder of that number, which is 0. The second number equals the remainder of that number, which is 1, and so forth. So that was exactly what we were looking for. And then I found out that you will have to use an inverse modulo based solution to calculate the Chinese solution for the Chinese remainder theorem. And that involved computing the modular inverse of two numbers. And so I have a few links here, a few resources if you want to watch. It's really useful. For example, for the modular inverse, it's a YouTube video of a teacher explaining visually how the modular inverse works. It's called Modular Inverse Made Easy, and it was really helpful for me to wrap my head around. Not completely, I don't think I fully understand what's going on, but at least know what's happening, get a sense of what's happening. With those, so it was modular arithmetic as well, greatest common divisor, Euclid's algorithm, they all had a play in this part solution. So with that in mind, I set out to write the solution. What I first did is I had an index to map. Let me add a breakpoint somewhere here. Yeah. So I can show you what those variables are. So first I had a bus index to map, which was basically an object with the properties of those objects being the bus ID, and then the value would be the index in the array. Kind of like it's the delay, the remainder that we had to look for. So bus 13 was at index 0, bus 17 was at index 61. If we go and have a look at the input, 13 at 0, and then 61, which was it again? Plus 17, yeah, 17 here is at 61 position in the array. So I did that so I could reuse later, and then I calculated the product of all the bus IDs, because that was the formula. So the mathematical equation we had to solve was this, where x is our answer for part 2, and this was the mathematical equation, which basically says sum all of these, and then use the modulo with the product but of the bus IDs as the modulo, which I'm calculating here. I'm multiplying all the bus IDs, and then this equation says, hey, get the bus delay of that bus, multiply it by the product divided by that bus, and then multiply it by the modulo inverse of that bus with respect to the division, this division. So that's what we're doing here at the very end. And we're using big int as well, because our numbers are so big, they're overflowing the max integer in JavaScript. So I had to use a big integer to not have them overflow, because we were having numbers above 9,000 trillion, which is about the max integer in JavaScript. So that's why I'm using a big integer. So here it's I'm using a reduce to go through the entries of the index map we just created, and then I'm multiplying the bus delay by product divided by bus ID, which is here. The product of bus IDs divided by bus ID, and then the modular inverse. So then I use I create a function to calculate the modular inverse, which is this one here, and it looks a bit cryptic. I usually never use variable names with a, m, and x, and so forth. But I have to say I kind of cheated a little bit, and I copied this from the Geeks for Geeks website, which is, I found it here in this link. I scroll down below, and there's a Python solution. I am not very familiar with Python, but I can read Python, so I was able to, let me find it. What's a Python solution? No, PHP, C#. Okay, Python, here it is. So this is basically the function that you're seeing here. Calculating the modular inverse is this one, is this function over here. And I kind of like use the neat trick again to swap variables, and I renamed some variables to make them more descriptive, but it's the same logic. I don't fully understand it to be able to explain it in a way that you'll understand what it does if you have no idea what modular inverse is. But just trust me, it does what it does. It computes the modular inverse, and then with that we can kind of like sum up all the sub-elements of the equation, and then the result was using the modulo to the product of bus IDs. So that was part 2. Very difficult. Spent almost the entire Sunday solving it. I was glad to find an answer, but finally find an answer. But I didn't like this part that much, because it was a bit part luck, I guess, because if you knew about the Chinese remainder theorem and what it does, then when you as you were reading the puzzle, you were like, oh yeah, I know what this is. This is the Chinese remainder theorem, and I know how to solve it. But if you don't know about that, about the theorem and the mathematical approach to it, then you're kind of left guessing, because you have no idea how to approach this. And so that's why I spent a lot of time Googling and trying to find a theorem that kind of like some mathematical equation that kind of like resembles the puzzle. But it wasn't necessary to use the Chinese remainder theorem, because I also found out later that there's a more elegant approach to solving this problem. And I actually found also a really neat poem on Reddit, someone explaining it. Yeah, I'm not gonna look it up now, but there's a different approach that is more elegant and involves less math than what I did. But yeah, anyway, let's hope day 14 is not gonna be as difficult as 13. Otherwise, it's gonna be a few hours on this stream. So without further ado, let's get on with day 14. If you have any questions, let me know. I hope I explained days 12 and 13 enough. If you want to have a look at my solutions, you can go to the repo and check them out. Yeah, let's get on with day 14. Docking data. So, I also forgot to explain. So this is kind of like the map that unveils itself as we go on with the days and advent of code. So we were here in days 12 and 13 on a ferry on an ocean. So this is like the line is the ferry's route, and like the squiggly arts here in blue are the ocean. So day 14 looks like we arrived on an island. So our puzzle is going to involve something that we have to do as soon as we arrive on the ferry port on the island. So docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry. So the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bit mask system. Bit mask leads us to a Wikipedia page. Yeah, bitwise operations, I'm vaguely familiar with them. Uses a strange bit mask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. I have trouble pronouncing this word. The initialization program, your puzzle input. So our puzzle input is the init program. It can either update the bit mask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bit masks for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. Well, yeah, that makes sense. It's kind of like an array. Your memory address is an array, so you tap into the 8th index and then you say assign value 11 to that index. The bit mask is always given as a string of 36 bits, written with the most significant bit representing 2 to the power of 35 on the left and the least significant bit 2 to the power of 0, that is the first bit, on the right. The current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. Okay, so I have to look at the input because reading the instruction is not that clear to me what this is about. So let's have a look at an example input. For example, consider the following program. So we have a mask here. So this is a 36-bit bit mask, and X doesn't change leaves the bit in the value unchanged, and 1 swaps it or something. Let's see what it does. So consider the following program: memory 7, memory 8, memory 7, memory 8. Okay, this program starts by specifying a bit mask, which is the mask. The mask it specifies will overwrite 2 bits in every written value. Oh, I see. So you write the value 11 to memory 8, and then it overwrites it using this mask. The 2 bits, the second bit, this one, is overwritten with 0, and the 64, I don't know what he asked how to pronounce that, 64th bit is overwritten with 1. Yeah, that makes sense. The program then attempts to write the value 11 to memory address 8. By expanding everything out to individual bits, the mask is applied as follows. So this is our value 11 in this 11 in decimal, and this in binary. 11 in binary, which is kind of like this, but then we like prepend with a bunch of zeros. And then we have the mask, and then therefore the result that we actually write into memory is 1. X doesn't change it, so we come 1 changes it to 0, so it's 0, 0 doesn't change, 0, 1 doesn't change, 0, so on. And then this one is changed to 1. And so then we end up with this number, which in decimal is 73. So because of the mask, the value 73 is written to memory instead of 11. Then the program tries to write 101, which is this, in binary. It masks it to 101 as well, because that's coincidental. This time the mask has no effect, as the bits it overwrote were already the values the mask tried to set. Finally, the program tries to write 0 to address 8, 0, which is this in binary, all zeros, and then the mask makes it into a decimal 64. So 64 is written to address 8 instead, overriding the value that was there previously. To initialize your Fairies docking program, you need the sum of all values left in memory after the initialization program completes. The entire 36-bit address space begins initialized to the value 0 at every address. In the above example, only 2 values in memory are not 0. In the above example, only 2 values in memory are not 0. That's true. That's values 7 and 8. 101 at address 7 and 64 at address 8. Yep. Producing a sum of 165. Okay, so I kind of understand what is going on now. We're gonna get our puzzle input. Let's have a look. So let's see. Execute the init program. What is the sum of all values left in memory after it completes? So we get a bunch of masks and a bunch of writes to the memory, and then we need to apply each mask to each write. So this mask applies to these writes. So we try to write to element 30,009 or address in memory 30,904 and so forth, these values, but these values are and then we need to apply the mask to these values. So first we need to convert these values from decimal to binary, and it has to be a 36-bit binary digit, and then we apply the mask to that binary, and then we get a new binary, and then we convert that binary back to decimal, and then the new decimal, that's the actual value that's written to this address. So we do this for each element, and then we get a new mask, so we use this mask instead for these elements, and so on until we reach the end. And then we're gonna have our mem array is gonna be our memory with a bunch of values in the addresses. So we need to sum all those values, and that's gonna be our answer for the first part. That's how I understand this puzzle. So let's save our inputs into our working folder in here, and let's remove the last new line of the input. There we go. So here's something to work with. What I'm gonna do as well, I'm gonna use the example inputs to kind of like test our solution. And it's also easier to debug when we're dealing with a smaller input. So it's easier to like go through to see what the code does. So I'm gonna grab the puzzle example input there. I already have the setup code copied from previous day, which basically reads the file. And let's go on with solving the first part. Let's see. We can get rid of this. Is our input? Okay. First thing we need to do is we have an array. Do we have an array? Well, we read the input. We don't have an array yet. We need to grab. Let's have each line be an element in an array, and then inside, and that element will be another array, which is gonna be split with space equals space, and the first element of that array is gonna be either mask or the memory address, and the second element is gonna be the mask. If it's a mask, it's gonna be the bit mask. Otherwise, it's gonna be the decimal value that we're trying to save into memory. Let's do that, and then I can go through each element in the array, and I can say if it's mask, then update. We're gonna have a variable that keeps track of the mask, the current mask that we are applying to the values. And so as we go through the array, it's gonna say, hey, is this mask? It is. Then update the bit mask to this one, and then to this one, and so on. And then if we don't find mask, but we find like a memory here, let me see. I can grab the value, that's easy. But what I need to do here is I'm gonna need to I need this number, because that's gonna be the index at which we need to assign the masked value from here. So I think I'm just gonna use regex to extract this number. I think that's the easiest. I'll use regex, or perhaps I can use a substring. I can use slice as well, because I know the first 4 indexes of the string is always going to be the same, and the last one as well. I can use slice. I think I can use slice to grab the number. Okay, let's do that. So input split by new line, and then each element we map them as well, which is going to be our line. What do we call the line? So the entire thing is init program, and each line is an instruction. Let's just stick with the instruction. And the instruction is going to be an array with the first element being the so I need to split it. Maybe not do it in one line. Instruction split by space equals space, and then our first element is going to be the masks or the mem, and here's the bit mask or that. Yeah, actually I can just return this. That's much easier. Yep. Okay, so we have our input parsed here and mapped in the way we want it. Let's name this instructions. So now we'll need to go through the instructions. For const instruction, for an object, for of array. I have kind of like I always confuse. So in JavaScript you can use for of or for in, and I always confuse which one is which, because you can use for of if to loop through an array or an iterable, and for in through an object. And if you use the one with if you use off with an object, it's gonna fail. So I have this trick in my head that if I say foreign object, like a foreign object, like a foreign object. So let me spell it out. Foreign object. Then so what I say is like for in. Oh, which means you use object with for in, and for off use an array. So that's what I could do every time. So I know which to use for off or for in. So it's an array, so it's for off. If it would be an object, it would be for in object. And then as we go through each instruction, we need to let's create an array here, or let's create some variables here. First, it's going to be our bit mask, and then it's going to be our memory. Yeah, so we have our memory and our bit mask. Why is it not what I want? Yeah. Other variables we need to track of? No, not really. We have our memory and our bit mask. And our solution is basically gonna be console log, well, you can say const sum is gonna be memory reduce accumulator value, accumulator plus value, and we start at 0. And then we do a console log answer part 1. It's gonna be the sum. So that's basically it. I jumped a bit ahead, but now what we need to do, oh, and then the memory is gonna be, let's instantiate that to an empty array. There we go. And then we go through each instruction, we get the bit mask, we apply it to the value we try to save, and then save that in the memory. So can I do, I'm gonna use a range instruction here, and I'm gonna say, what do we call this? It's like mask or mem. What do they call it in the puzzle? Bit mask. Well, I can say this is like the what is it? If you have an assignment expression, what's the left hand side and what's the right hand side? So it's the value of an assignment expression, the value of the right side. Yeah, but I'm trying to come up with a useful name here. Yeah, I'm just gonna say the value is gonna be the second part, and this one is gonna be do you have any idea what I can call that? Something descriptive? I have no idea what to call it. Assignment expression left part causes the expression on the right hand side to be evaluated. If the left hand side is a variable, the value of the right hand side is assigned to that unevaluated variable. Yeah, let's use variable then. So if variable equals to mask, then we have a new bit mask, and we say bit mask equals value. That's good. And then we can break, or no, we don't need to do that. We can have an else in here. Else, then we know this is going to be a memory, so we need to grab this index here, and I said I could do it with slice, so I use this neat little program, run.js, kind of like to test JavaScript code and so on. So I'm gonna use this as a string, and then slice 4 minus 1. Yeah, 4 0 1 2 3 4. We're here, so start here, but not 0 1 2 3 4. No, start here at 6 and go up until -1, so it kind of like wraps around the end. And then yeah, I think that will work. And then we need to cast this to a number. So it's gonna be const original value is gonna be value slice 4 minus 1, and then this is a number. Slice 4 minus 1. Yeah, that looks good. So we have our values here, and then what we need to do now is transform this decimal into a binary, and then apply the mask and then transform it back to a decimal. So let's figure out, I haven't done this many times, or like I'm not very familiar how to do that, but I'm just gonna Google it. JavaScript decimal to binary 36-bit. How do I convert an integer to binary in JavaScript? So that's kind of like, if I don't know something, I just Google, and really like good programmers with years of experiences are just very good at Googling stuff. They know what keywords to look for to get an answer as quickly as possible. And you do that all the time. No matter how many years experience you have, 10, 20, you've been programming for your whole life, you can't possibly know everything that it's by heart that you have to do in your programming life. So you always be Googling stuff and forgetting. So, but it doesn't matter how you solve it as long as you solve it. So Googling, looking up and searching stuff is a valid way to get paid for being a programmer, because you know how to Google. So what does it say here? Why is this answer not accepted? I tend to be a bit skeptical about not accepted answers because there might be something wrong with them, but I'm not sure. I also look at the comments. This one has 8 upvotes and an explanation. Okay, this seems legit. So it's using a bitwise operator. So des to bin, 1 is 1, minus 1 is this. Yeah, but that's not what we want. We want to kind of like have, because how are we gonna apply the bit mask? I'm sure there's a neat way to apply the bit mask as well. Pretty sure of that. In JavaScript, you could maybe use the bitwise operator to kind of like apply a bit mask to another number. But let's first search how to convert our decimal into binary. We can use parse int. That's true. That's true. So what do we get if we do parse int 61913? Or let's not use this number. Let's use this number because we already know. And then into binary. 3. No. Decimal. 11. Wait a second. Base. Yeah. Oh, returns the decimal value. No, I want the binary. Binary. Well, that's not what I want. To string instead of parse int. What does this person ask? What the? Nope. So still looking up JavaScript binary to decimal to binary. Yeah, so this kind of like a technique. I'm just looking for a shorthand. I'm sure there's a bitwise operator you can apply. Oh, here they're using binary to decimal. What does it do? Oh, it does way too much. No, I'm hoping there's an easier way. Here, there's a guest. Maybe that. Wait, isn't there like a native function? Yeah, I mean, I should have gotten a native function, but maybe there's not. Let's look up. If I'm looking up decimal to binary in JavaScript, I should have gotten one of the first results should have been the native solution to this. To fixed, to string. Nah, not really. I don't think JavaScript has a binary conversion. But I know there's helper functions library. I could import Lodash to do this for me. Oh, here, binary to decimal. No, I need decimal to binary. Decimal to binary. Convert base. Where's convert base come from? Here, base from parse int to string, base to. Oh, I see. To string. So maybe I can say to string and then 2. Oh yeah, this is binary. Neat. Okay, and then convert base. What does it do? Convert base decimal to binary from 10 to 1. Oh, okay, that's pretty straightforward. So we have our binary here. It's a string though. Are we gonna work with strings? Let me think, because this is a string as well. So we have our string in here, and then we pad the string with enough zeros so we have the same length of this one. And then how are we gonna apply the mask to, how are we gonna apply the string, the bit mask to another string? Let me Google that a little quick. Apply bit mask JavaScript. See if there's like something like a trick we can use as JavaScript. Bitwise operator, bit masks. So JavaScript has 7 bitwise operator. Yeah. For a simple bit mask, we'll need only these two, or and this or this one, and. Oh yeah, I know. Yep. Wait. I'm gonna look up the MDN. Bitwise. MDN. MDN is Mozilla documentation for JavaScript. I always refer to it as the authoritative, original, most comprehensive way to read about the official stuff that JavaScript has, the language, like methods and data structures and so on. So bitwise OR operator returns a 1 in each bit position for which the corresponding bits of either or both operands are 1. So we have A and B, it's going to return and. So what are we looking for here? We're looking for when we need to, let's first, let's go into our, here, let's grab this one, have it a string, let's grab this one here as well. So we have, and then let's pad this with 0, enough zeros. Okay, so what we're looking for is we need an operand, hopefully we're gonna find one, that they're kind of like, this needs to be left unchanged and this needs to be overwritten. If it's an X, then just return this value. If it's a 0, then, or 1, return whatever that is. So return, so our solution here is gonna look like this. Bunch of zeros. This is gonna be 1, this is gonna be 0, 0, 1, 0, 0, 1. Yeah. So if it's an X, return this. So that's what we do here. If it's a 0, return 0. X, X, X. If it's a 1, return 1. So kind of like, yeah, okay, let's see if we find an operand for that. The OR operator returns 1 if either of those are 1. So 1, 1, 1, and then it's 0. That's not what we need. That is not what we need. Let's see if what bitwise AND, I think it does the both. If both ones are 1, then 1, otherwise return 0. Yep. I'm not sure that's gonna work for us. What is not? The bitwise NOT operator inverts the bits of its operand. So, oh, it's just inverted. No, that's not what we're looking for either. What does XOR do? Returns a 1 in each bit position for which the corresponding bits of either but not both operands are 1. So if both are 1, then it's 0. If either of them are 1, then it's 1. Not what we're looking for either. And then you also have OR assignment, and then assigns them. Oh, is it just the same? So we went through all 4 bitwise operators in JavaScript, and OR not or XOR is not what we're looking for. So let's go back to Googling. So this person is applying a bit mask somehow. AC. So A is this, C is that, or then you have a mask. Wait, so if it's 0, regardless of this is, it needs to be 0. Let me think here what I can do. I'm thinking if there's a way I could just catching up on chat now. Did you see the tweet by Eric regarding what software development is? I did not. Let me have a look. Software development is 20% requirements gathering, 30% planning, 15% design, 40% problem solving, 35% testing, which I'm not doing, 18% operations, 4% looking up the arguments for tar, 30%, I'm pretty sure we're above 100% here, writing documentation, 60% debugging, 7% installing updates, 2% actually typing code into an editor. Yeah, that's funny. So you're watching me, the stream, you're watching me basically for 2% actually typing code, and 98% of the time I'm just looking up stuff and figuring out what to do. Yeah, so if you came here for some movie action hacking type of stream where I'm just typing and hacking stuff, no, that's not what this is like, because that's not what real programming is like. It's just problem solving, yeah, thinking, and trying to come up with a solution. So here we have our mask. Well, I'm trying to find a way if there's, can I map this mask to something else, that in which case we're going to be able to use one of the bitwise operators. So can I like transform the mask? Where's our mask? Where's our mask? Oh, here. Yeah, so can I like transform our mask to something else from which we can use one of the bitwise operators to both of these, and then kind of like end up with this? That's something I'm trying to think of. What we know is that whatever value is in the mask, that's the authoritative value. That's going to be the value that we need to end up with, regardless of whatever our number has. So if this is a 1, it's always going to be a 1, regardless if it's 0 or 1, we don't care, it's always going to be a 1. So which bitwise operator gives us that? That's going to be OR. OR returns 1 regardless of what the other one returns. But however, in case it's 0, we want it to be 0, not 1. So then whatever it is returns 0. So for this case, we don't need the which bitwise operator satisfies this condition. So return 0. It's gonna be and, not and. Well, and. No. Yeah, and. Because if this is 0, both are zeros, therefore it's 0. If this is 1, with and, this is also going to be 0. And yeah, so yeah, this is always going to be 0. So here we need the and for this one we need the the OR. Can we somehow apply the mask twice? So can we like parse this in a way that we're only left with the ones, and then apply that with, to our value with the OR bitwise, and then do a second round. So we apply the AND where we're left with the zeros and apply the AND bitwise. So that's gonna, and then we're gonna end up with this. Can we do that perhaps? Maybe we could. Maybe we could. I'm gonna give it a spin in here. So we have our this. Let's call it const mask. So mask replace x's with zeros. And then oh, replace all. Can I just replace all? Yes, I can, because I'm using node 15. Awesome. And then, so we're left with the ones here, so that's good. Let's add a space here. And then we want to apply the AND operator to our value. So we apply the AND operator, bitwise operator, to our value, and our value is this. Let's assign it const value. It's going to be a string. I wonder if I can use bitwise AND operator with strings. What's going to happen now? Hey, we do get a decimal. So what is we do get a decimal. What is, let me go binary to decimal. I'm just gonna grab a quick utility here. Enter binary number. So what is no, we are looking for this number. So what is what do we end up with? I think we end up with this, but then this is 1 as well. Yeah, convert. No, it should give us 75 if I'm correct. I have no idea what is 576. It might be just a string problem. So I'm just gonna wait. How do you even use the bitwise operator? You have a decimal, and yeah, you can use it with numbers. Okay, so actually we don't even need to parse the decimal here into binary. You can just use it. So let's say const value decimal, which is 11. Was it 11? Yeah. So value decimal, and then we need to, oh, I see, we need to okay, we replace that into a string. So what do we have? The mask. Okay, we need to kind of like parse this to a number. Can we, from decimal, use parse int and base 2? Let's see what this returns. 64. That's correct, because we have this binary 0 0 0 0. Convert. That's 64. Okay, so we have a number here, and applying the bitwise operator over this should return 75 though. Oh, I wonder what's going and I don't think it was and, was it? I think it was or. It was or, not and. Yeah, okay, 75. That's the one we're looking for. And so we did one round of masking. Let's do the other round where we have the zeros left in here. So let's replace mask, replace all x's with ones, because then we know, yeah, that we have zeros left. and then we need to parse that into a string, into an integer. I hope that's not gonna overflow. Hopefully not. And then let's say this const new value. Then we need to apply the AND operator for a new value, and we get 73. Is that correct though? 73. Look at that. And if we use 101, 101. I think that's our solution over here. Awesome. Okay, let's put it back in our code here. So I'm gonna copy paste what I wrote in here. We have the original value. So original value is gonna go in here. So our mask, we replace it, we parse it into a decimal, we apply the first bit mask, which is our new value, and then we kind of like need to apply a second bit mask. So we can name this new value in lack of better variable name, and then we apply the bit mask to the new value, the AND now, and then we get the new value, and that's the value we need to save to our address, which is going to be memory. Oh wait, this is the memory address. Memory. This is the address. Memory address. I'm using the wrong number here. Memory address equals new value. But then the value, this needs to be the variable, and then we use the value here. Then we have the new value. Question. I can use the bitwise or AND operator, can't I? Or was it? Or assignment. So this is kind of like or assignment A or assignment 3. Does it do what I want? So can I like replace this with? Oh no, it's gonna overwrite the original value, but that's fine. We don't care about it. That is fine. So can I just do? I'm trying to think if I can like refactor this a little bit. Maybe I can do both in one line. I could, but it's gonna make it. Does it matter in which order the bitwise operator is applied? So if I switch these two around, does that matter? It shouldn't, I think. No, it doesn't. No, yeah, it doesn't matter. So I can just say, let's put this up front. All right, and then we can say AND in here, and put this one in here. Kind of like this, no? So new value is going to be the value with the bitwise operator, with the OR bitwise, and AND with bitwise of these two in succession. Does this do what I want it to do? Let's see. And then new value. Yeah, works. And then I can just assign it to the new value. So I can just say, let's say this is a let, And now I can use the assignment operator here, and then console log value decimal. Yeah, that works as expected. So I can just shorthand this. Oh wait, but that's a constant. Yeah, then let's just stick with this masked value. We'll call this, and then memory disk. I think that's what we're looking for. Let's run our program with the example input and see what answer we get. Some node day 14. 4 is here. Index.js. We get an error. Mask is not defined because it's bit mask. Try again. Replace all is not a function. Oh, because I'm not using node 15 here, am I? Nope. I do have it installed, so I'm gonna say npm ls, and then I'm gonna say npm use 15. Can I just say 15? Now using 15. Awesome. Let's run it again. Nope. This one. Okay, so we get 165. Is that correct? 165. Yeah, okay. Let's run it with our input. Replace that here and see what answer we get. A minus value. That's not correct, is it? Maybe it is. Yeah, maybe it is. It can be a negative value. Why not? Not the right answer. Okay, then we might be having a overflow issue. Because the numbers are so big. Well, they're not that big. Wait, there was something in the puzzle input that I did not really do anything with it. The bit mask is always given as a string of 36 bits, written with the most significant bit representing 2 to the power 35 on the left and the least significant bit 2 to the 0 on the right. I wonder, let me see, how is binary JavaScript, how does it work? I think JavaScript uses the most significant bit for the plus or minus. So maybe you need to do that, something with that. No, that's strings. Binary JavaScript. (64-bit). JavaScript number is a double precision 64-bit binary format. No, I don't think it should matter then. I don't think it should matter. Let's use the debugger and see what is happening. I'm gonna add a breakpoint. Where do I want to add a breakpoint? In here. And then let's run it. So, oh, that's weird. It never gets to this point. Okay, I'll try to figure that out. Let's split this to the right. Okay, so why does it never get here? That's weird. Memory address. I think that's fine. It doesn't need to be a number though, so I think I'll just stick with it. Masked value, memory address, memory reduce, calculate. That's all right. Masked value is a decimal. Yep. does it run? Oh, perhaps the debugger uses node 14. That could be the problem. How do I change the node version of debugger? I can just say nvm. Let's see. I think default is okay. Let me just change the default to 15. nvm alias default 15 .3.0. Okay, so now our default node is 15, I think. Let me close the terminal, open up a new terminal, and then node version is 15. Okay, so I changed the default node version, and I hope VS Code is gonna pick it up as the default. So I'm gonna reload it, and we're back, and then let's run it again. Oh, here, replace. Oh, it's not a function, so it's using 14 for some reason. I wonder why. Maybe I need to quit VS Code completely. Let's do that. I'm gonna quit VS Code and I'm gonna open it again. All right, we're back. Debugger. Oh no, here debugger. Breakpoint still there. Go. Yeah, great. It's using 15 now. Awesome. So we passed our mask. So our bit mask is that. That's good. And then our memory address is 30,904. That's good as well. Our value is 804. Oh wait, it's not a number. Is that maybe tripping? Nah, it shouldn't though, because we got the first. Oh, we're parsing the int as well. So no. Here. Let's just turn this into a number. So we are. So then masked value is this. And then we save it to the memory address. So we get this masked value, and I wonder if it's I wonder if our problem is because JavaScript numbers are 64 bits and we are applying a mask of 36 bits, of which the last one is the most significant bit on the left. Yeah, but does it say anything about the positive or negative? No, not really. Let's see. Okay, let's figure out if this mask, disk mask, this mask, and 804 value is what we want. Let's turn 804 to binary. This is our binary. Let's pad it. Yeah. Okay, and then we have our mask, we have our value, and then we need to figure out the intermediate steps here. So let's say What does this do? And what does that do? But then let's apply it to a string. Yep, that's what we want. So in here, so with this mask, we replace all the x's with 0. Yeah, looks right. And here we replace all the x's with 1. So that's 1, 1, 1, 0, 0, 1, 1. Okay, so that looks good. And then we apply, first we apply this mask with the AND operator. So let's see how that looks like. With the OR operator. So let's say value. No, let's. I'll just use 804 over value decimal. Yeah, let's move this to the top. Okay, value decimal or operator here. Then we get this. Let's let's wrap this in a string, and then I can't do that for some reason. So this is the actual value of the first I'm gonna leave it like this. I wanna see how do I convert this to binary? Why is it so hard to convert this to binary? I just want to have it's a minus. Okay, let's assign this to a variable and then use toString. Okay, here's what we want. So this is obviously not right for some reason. Okay, so something is going wrong here. We have our here's our mask. The first mask we apply to this value. Let's it's a bit confusing for me. Let's remove this. This is mask value. Okay, so this is this. So the value of is this the binary that we needed? No, this is the binary that we needed. Value, but doesn't. Yeah, this is the binary that we needed. Let's just print it out here. Console log. Just console log. Value. All right, there we go. So we have our mask, we have our value, and we have our value in decimal. So let's just print our value in here, value binary, and then let's print our mask to the bottom, console log mask, and let's say this is value. Not actually. Yep. Okay, so this is our value, this is our mask, and then this is the first part of the mask, this is the second part, and then we and then we apply the first part and we get this result. So I'm gonna console log this in here, const first mask. Let's reuse this in here, first mask. That's good. And I'm gonna console log first mask. Okay, so this is our value, this is our first mask, and we end up with this. Is that correct? We're using the which bitwise or 0 0 is 0, 0 0 is 0, 101 is 1, 0 1 is 0, 0 1 0 0 1 1. But it's kind of missing all these numbers. Why is it not? That's the value, that's the mask. Okay, so we have our value. I think it's not applying all the. I think it's just because the value kind of like stops here. Yeah, I see what's wrong, because our decimal value in binary stops here. Even though we are padding it with zeros, and like in our examples here, I don't think when we use the bitwise operator that it does actually pad it. So as we can see, it applies the map. It applies the map for these numbers up until here. So this one is we're using the OR operator. So this one is 1. That's true. This one is 0. What does OR operator do again? Returns 1 in each bit position for which the corresponding bits of either or both operands are 1. So if this one, then it's okay. I got it. So this one is 0 0. This one is 1. This one needs to be 1 as well. Okay, something's wrong here. This needs to be a 1. Okay, this is what's wrong. Yeah. Somehow it's not. I don't think it's. I think if the mask is larger than the number, it's not applied correctly. So we either have to. Okay, let's Google this. Bitwise JavaScript. To string. This is a decimal. Maybe. What if I leave that to an integer? First mask is gonna be this number. Yeah, what if I leave that to an integer? Oh, well, yeah. Okay, that makes sense. When we log it, we need to log it to string. Okay, so it is using the integer here. And so now our mask is this, which is still not correct. 0 0 1, this needs to be a 1. Oh, I'm a bit stuck here. How do I? I'm sure it has something to do with the fact that our mask is a 36-bit integer. Binary, I mean. And a string of 36 bits. And that JavaScript is using 64. think that's kind of like the source of a problem. Because let's see, we have the value decimal is 804. We have the first mask, which is we replace all the x's with zeros, and then that's our going to be first mask decimal, and then we have x value decimal with the OR operand. So value decimal, the binary representation of value decimal is this, or I can just say to string to, yeah. This is the binary representation of our decimal number, and this is the binary representation of our mask, and then it's applying the OR operand for these two to come up with this binary representation. Is it maybe because is it starting at the top instead of on the right, because this one is not padded? How does it do? How does it apply the bitwise operator to two binaries that are not equal in length? Let's see. This is 0, this 0, this is also 0 for some reason. Or it needs to be 1. So maybe it starts from here. 1 or 1 is, you know what's weird? What's the minus doing here? First mask, x to string. I think, oh, because the last one is assigned. Oh, I see. In JavaScript binary, the most significant bit is assigned. Okay, let's here. A number only keeps, okay. This is tricky. To fix, returns a string representing the number in fixed point notation. To string returns a string representing a specified object in a specified radix. Overrides the toString method. So that's what I'm doing here. I'm doing number to string and radix 2. So let's, what's x? So x is this number minus whatever. So this represented in binary is this, but then with a minus up front, because I'm just curious how this leads to this. I have no idea what happens under the hood. Because 1 and 1 is 1. Maybe that gets lost. 1 and 1 is 1, 0, 0. So 0, 0 is, yeah, so that's not it. And if it starts here, 1, 1, that should be 1 as well. So it doesn't start from the right hand side, it doesn't start from the left hand side. It's just like somewhere in between. So what we are looking for, if we have Where's our here's our mask. Where's our first mask? Here's our first mask. Okay, so this is our first mask. So when we apply the original mask, okay, so when we apply this to this, we should get a sequence of, with the OR operator, we should get these numbers, well, just this, and then the ones, whatever the ones are from here, they should replace the zeros. So that would be another one in here, and I'll kind of like everything up there. So where do we see 11 0 0 1 11 0 0 1 0 1? No, nope, can't find this pattern here. So what we need to get is let's see, we need to get kind of like need to get this number, this binary number. So our result that we want to achieve is 1. Let's move the mask up top here. Okay, so this the number, this the mask. 0 0 0 0 1 0 1 0 1. It's good, leave untouched. So here we just copy this, paste in here. That's basically this is the number that we want to end up with on the first mask application. And for some reason we are getting this instead of this, and I have no idea why. Let me think. The bit mask is always given as a string of 36 bits. Maybe it has to do in how I convert this mask to a string. Because what do I do here? Where's the mask? Here's our mask. What I do is I replace, and then I parse the int. But maybe I need to pad it. Okay, let's maybe I think that might be the source of our bug. Let's try this. Let's grab the mask, for example, input, which is here. Here, this mask. There we go. And then so our mask is here, and then we replace all the x's with zeros, and then we get 64. That's correct, but what if we change this to 1? We get a very large integer. What is this integer in binary? 1 0 0 0. There should be another 1 in here. Oh, here's the 1. I'm trying to figure out if the parsing from string to a number of the mask, of the bit mask, is correct. It should be, because it's not. mean, if we have, let's say, and then let's replace all x's by 1, just like replace everything by 1. Yeah, replace all x by 1, and then also all zeros. What's the largest number we can get out of the mask? This one. So if we get a mask that has all ones, everything is 1, then this is the decimal representation of that mask, and it's well within our max integer boundary in JavaScript, because this is 9,068 billion, and max integer in JavaScript is like 9,000 trillion. So there's nothing wrong. The bugs, so there's like, when we parse this string into decimal, this should work as expected. Then we get a decimal number here, and then we use that decimal to, with the bitwise OR operator, to our original value. So original value. Okay, let's go back to this. I'm gonna clean this up a little bit. So that's the mask. That's the value in decimal. So let's do that. Const value decimal 804. Value binary. This value decimal to string. Okay, so then we have console log mask, value decimal mask, and then the first mask is this number, so the first mask decimal, and then we're gonna have our first mask, which is gonna be this. First mask decimal. Kind of like trying to print out all the values here. Second mask. Clean this up a little bit. And then second mask decimal. Lars, do you have any idea what's going on, or any other viewer if you're watching? Maybe it's something I'm missing. If you want to give me a hint, I would very much appreciate it. I'm sure there's something wrong with the fact that JavaScript is not using 36 bits, and somewhere in our bitwise operations something is amiss. That's second mask, and that's going to be parse int. There we go. Okay, and then we have const first pass value decimal and first mask decimal, and then let's console log okay, let's console log let's get rid of this as well. Okay, so our value decimal is 804, but we know that our mask is, we know that as well. Let's log console log first mask and and the decimal, first mask decimal. So that's our decimal, the first mask. Decimal representation. We can do that for the second mask as well, but let's leave it at that for now. And then let's move our first pass here to the top, and then let's console log first pass. So that's our number there. So it's basically saying console log value decimal and first mask decimal. So these two used with the OR bitwise operator returns this decimal. Which for me in decimal, if I look at it, it's doesn't make any sense, and which is, yeah, it doesn't. We need to look at them in binary form. So let's see, let's print them out in binary form. Console log value binary, and then console log first mask, and then console log const first pass binary, first pass to string, and then first pass binary. Right, so this one applied with this one with an XOR operator bitwise is going to return this one. Yeah, that's where we left off. So that's, yeah, that's not the correct thing. I wonder what we need to do, how we need to change our mask or our value to have it apply correctly, the bitwise operator. Our value is 804, our mask is 54. So I think the mask, we're using two decimal numbers, so I don't think this is wrong. I think the computer does the right thing. You give it two integers, it's applying the OR bitwise operator, it's going to return this number. That's correct. I think what's amiss is that our decimal representation of the first mask should be different, should be a different number, decimal number, so that JavaScript does the right thing. But what should it be though? Because this mask is this decimal, that's correct. This is a decimal number, and we have a different decimal number, and then we get this. Maybe that's correct. I don't know, we don't even know that's wrong. Maybe that's correct. Let's go to the second pass. Do we get more inputs that we can play with? No, or just this ones, because it seems to work for smaller values. If we use 11, 101, and 0, if we use, if we use 11, we can do that in a bit. Let's do the second pass. Let's move it up top, second mask, and then we can say const second pass is first pass using the AND operator of the second mask decimal, and then const second pass binary is second pass to string. Here we go, and then we console log log these as well. Second mask decimal, and then we go to the first second pass, and let's log that here. First pass, second pass, second mask decimal. Yep, and then so these two decimals applied with the bitwise XOR end up with this number. Okay, let's use more comprehensive numbers and masks for from our example input. Okay, so our final answer is here. Let's get rid of this line. Our final answer is here, 73 for 11, which is correct. And for 101 is 101, and for 0 is 64. So 101 is 101, and for 0 should be 64. So we get the correct answers here. Let's say, so for 11, the first mask is this, and the decimal is 64. Well, that doesn't matter, so we apply 11 with 64. We get 75, which is not a negative number. Maybe the negative number messes up with our solution. If the number is big enough, it becomes negative for some reason. So maybe that's the issue. Maybe that's the issue. And then the second mask is this one, and or in decimal it's this. So we apply these two decimals with the bitwise and then we end up with 73. Yeah, that makes sense. Let's instead of logging the decimals, let's log the binaries. First pass binary. So we apply this to this. We apply this mask to this with the AND operator. So we end up with no second mask. No, we apply this one. And then we end up with this. There it is. So this is the mask we apply to this number, and then we end up with this mask number using the AND bitwise. So 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1, and so forth, and then it stops. Then we don't really care about these. Yeah, we'll discard them because they're as big as the number. Oh, I think I see what's wrong. I think I spotted the problem. I think, let me see, if we have a big number, so this makes sense because this number is only that big, so we kind of like discard the rest. let's add another console log here that says and bitwise. And bitwise. Okay. If we use, let's say we use 0. On our first pass, we're gonna have an OR bitwise. We're gonna use the value in binary. Value binary is here, and then the first mask is this, and then the result first pass is in binary is this. So 0 in binary is 0. This is our first mask that we apply. So then we add 1 to that, and then we get 64. No, that's correct. 0, 64, 64. Let's say value binary, and then value first mask decimal first pass value decimal. I'm gonna print them next to each other so then it's easier to kind of see. Okay, so this in binary, this in decimal, applied to this one in binary, this one in decimal, leads to this one. Okay, that makes sense. Okay, let's do the same thing. First pass binary, first pass, second mask decimal, second pass. Get rid of this last one. So same thing here. This one applied with this mask with the bitwise is leads to same number unchanged in decimal and therefore also in binary, because, well, yeah, the 0 was already 0, so there's no shift there. Okay, I think we have now something a bit better that we can debug with. Let's grab, so these are all the inputs that we get to work with. Okay, so let's go back to our original input. Let's grab the mask and let's grab the decimal. Okay, so this binary applied to this mask results in this mask. Why though? I get no idea why, or bitwise. So 0 and 0, let me think. So this is the mask, leave the first unchanged. So this unchanged, that's good. Then they leave the second one as changed, so that's unchanged, that's good. And then this one, make it 1. It's 1 already, so that's not changed. The fourth one from the right should be 1. So it's 0, it should be 1, but it's still 0. This should be 1. For some reason, it doesn't apply. Let me think. Value decimal is 804. First mask decimal is this big number. And then first pass binary is, first pass decimal is this. Why is this a negative number? And what is happening with applying these two? Is this mask too large, perhaps? it would be nice to kind of like get a an under the hood. Oh, I see. Wait. I should here. The operands are converted to 32-bit integers and expressed by a series of bits. Numbers with more than 32 bits get their most significant bits discarded. Oh, I see. For example, the following integer with more than 32 bits will be converted to a 32-bit integer. So the rest is discarded. And these are 32 bits. Let's confirm that. Length 32. Oh, I see what's going on. This our mask is mask.length is 36 bits, as it says in the puzzle. And so JavaScript discards the last 4 bits because it's 4 bits longer than it can deal with. So that's why these 4 aren't really applied in the mask. Okay, so we need to figure out how to apply bitwise operator to something that's more than 32 bits. Okay, let's read on. Maybe the clue's in here. Okay. Google bitwise 36-bit JavaScript. Bit JavaScript. I saw 36 here somewhere. Now consider what happens if you add one more f to the values. In the case the values are 36 bits all set to 1 and the result should also be 36 bits all set to 1, but no. Both the a and b values are converted to 32-bit values. Yeah, beyond 32 bits. So what happens if you try to work with bitwise operators on values that aren't representable as 32 bits? To do this, the JavaScript interpreter calls the internal toInt32 function. You can't use this in your programs. This performs an intelligent conversion to a 32-bit. It ignores all fractional parts by truncation. If the value is larger than a 32-bit integer can store, then the result is 32 bits all set to 1. So, okay, this explains it, but how do we deal with it? How do we deal with that? Bitwise 36-bit, so we need a way to use the bitwise operator for bigger numbers than 32 bits. Is that even possible in JavaScript? Is that even possible in JavaScript? Apply bitwise operator 36-bit JavaScript. If is there a way to convert a 36-bit into 32-bit? Convert 36-bit to 32-bit. Maybe we need to do that first. How to convert the decimal number 36 to 32-bit single precision binary float. JavaScript. How to convert 36-bit binary to 32-bit binary in JavaScript. I believe that's even possible. Is that even possible? If you have a number representing 36 bits in binary, how do you represent that number 32 bits? That's not possible because you're going to lose some significance. Nope. So that's a silly thing to Google for. Let me think. But wait, we can represent it in decimal though. Okay. How do I convert a 36-bit binary into a decimal that's well, that's what I'm doing here, aren't I? Our mask is 36 bits, and what we do is convert this into a decimal. First mask, this one. So I'm gonna go and say binary to decimal. Binary to decimal. Oh, I think we have it here as well. Enter decimal. No, binary decimal. So this binary returns this decimal, and in JavaScript we do have that decimal. Since we do the conversion to decimal, I don't think it matters that the binary is truncated because we have two decimals here. And then, or maybe second mask decimal. First pass is also decimal. It all happens in decimals though. And what does the JavaScript do under the hood? It converts the operands to 32-bit integers. So these two decimals are converted into 32-bit binaries before they're applied with the OR bitwise operator, which is all right, no? Because this number can be converted, or can? Oh wait, it can't. I think decimal to binary. We're gonna get this binary, which is how many bits? 36. Yeah, so that's where our bug is. JavaScript tries to converts this decimal into a binary, and because the binary is 36 bits and JavaScript only deals with 32 bits, it discards the last 4, so then we get a weird number here. How do we make sure that we can use the bitwise operator for large numbers? JavaScript, use bitwise large decimal with large numbers. To solve this problem, you could use big int. Let's try and use big int. So what is it saying? Big int, and then downcast it back to number. So 39, big int. Okay, maybe that works. Let's try and use big int. I used big int yesterday as well. I didn't know you could use bitwise operators on big int, but since you can, maybe that'll work. First mask decimal, let's say big int. And then value decimal needs to be big int as well. So then we have our first pass, and then first pass here, second mask decimal needs to be big int. Okay, so we have a bunch of big ints here, and then at the end, let's typecast it to a number. Second pass. So it's this number. I think this looks much better now. Yeah. Okay, let's do that. Let's move this to the right. Okay, we'll have to use big ints. So our value is a number, but let's turn it into a big int. And then this needs to be a big int. And this one as well. Can I just make this more readable here? All right, so we have our big ints here, and then at the end we need to downcast it back to a number. It's gonna be fine because numbers are not that big. Oh, here, we're missing a parentheses. All right, let's try our solution again. We get a very big number that looks maybe a bit more correct. The answer is too high. Wait, did we overflow? I don't think we did. Thousands, million, billion, 12 trillion. No, we didn't overflow. Let's see if how our input runs with how our program runs with the example input. 165. Still same thing. Okay, and then let's try and debug it, see what's happening. Let's run through it with the debugger. All right, so we have our value is 804. A memory address that, and the masked value is this big int, and then we cast it to a number before we assign it to the memory. So let's go to our memory is empty now, and then let's go to the next one, and our memory should have yeah, it has that value at address 30,904. 30,904, yeah, that value. Okay, so we go again, and then we have this value now, and the masked value is a big int as well. We assign that to the memory, different place. And then we have that value at that memory address. So that's good. So now we have 3 values in our memory, and then now the mask should be changed. The bit mask should be different. Yep. We updated the bit mask. And now we have a memory address of this, the value is this. And our mask value is a big int. That looks good. This looks good all the way down. I don't spot an error here off the bat. And then let's see what we end up with. What's our memory look like? 6,541 elements. No, 481. Which kind of like should be 60. Wait, how many? How big is the memory? 65,000. Yeah, that looks good. There's no memory addresses that are bigger than that. So it's not like we're out of overflowing the array or something. Everything is smaller than that. So I think all the values are being saved. And then what we do is we sum them up. We sum them up. But maybe that's a lot of values. Maybe we need to use big int. Although, no, it shouldn't really matter. Big int 0. Big int. No, I don't think it matters. Yeah, no, it doesn't matter. Same number. Am I reading it correctly? So, I think so. The bit mask is applied before the number is saved. So you have 11, you apply the mask, and then you save it. You have 101, apply the mask, then you save it. And then here, wait, this is the same memory address. So does it overwrite the previous, the mask? Okay. So because of the mask, the value is okay. 101 to address 7, but then it applies the mask doesn't change it. Finally, the program tries to write 0 to address 8. 64 is written to address 8 instead, overwriting the value that was there previously. So we do overwrite it, and which should happen here in this case. We should just, yeah, overwrite the value. To initialize your various docking program, you need to sum the sum of all values left in memory after the initial init program completes. The entire 36-bit address space begins initialized to the value 0 at every address. 36-bit address space? I wonder if I have to big int the memory address as well. I don't think so. The entire 36-bit address space begins initialized to the value 0 at every address. At every address. So I go through, oh wait, maybe that's what's happening. I need to because we end up with an array with empty values. So if value, then add it. Otherwise, return accumulator. Maybe that's, no, that didn't change anything. because if it's 0, then it's gonna just skip it anyway. In the above example, only 2 values in memory are not 0, 101 at address 7 and 64 at address 8, producing sum of 165. The entire 36-bit address space begins initialized to the value 0. Yeah, we don't care about that. We just care about the values that are present at the end of our program, which is always in here somewhere. What is the sum of all values left in the memory after it completes? That's interesting. So this number is way too high. We need a lower number. Somewhere we're ending up with too big number. Maybe going back to our bitwise big int. Maybe something that we're doing is wrong. Well, let's check it out. Let's so this this binary masked with this binary returns 0 0 1 1. That's correct. So we change this 0 to 1, then it's 0, then it's 1. That's good again. And then it's 0 0 1 1, and here's where we reach the end of our number in terms of binary significance, and then everything else from here is just copied over. That seems correct. And then on the second pass we do an AND bitwise. So we have our mask is X, leave untouched. Yeah, so this is 0 0, this is a 1 1, this is all 0. Let's print our mask in here, or just like this. Let's print our mask in here. So let's do it like this. Our mask is that, and then the value we start with is this. Log. Nope. And then the value we end up with, console log mask. Yep. And then the value we end up with is in binary is second pass binary. There we go. So this is what we start with, this is our mask, and this is our final result. Let's see if it's correct. XX says leaves those untouched, so we just copy 0 0 here. 1 1 means turn those into 1 1. Whatever they are, that's good. 0 0 means 0 0 1. Leave this untouched, which is 1 2 3 4 5 6 7 8 9 10 11 12. 1 2 3 4 5 6 7 8 9 11 12th. 12th is 0, so then it's 0, so then it's, yeah, everything's 0 for X here, X0 X0 X0, and then the ones and zeros are just copied over. Looks correct. Looks correct to me. And then we get this number in decimal, and this number we store into the memory, which is what, 1,000 million, 54 billion. 54 billion. So there's a bunch of numbers. Let's run our debugger again. So our memory has, oh wait, why did it, there's an error? No. Why is it not breaking where I want? Nope. Output. Is it using node 14 again for some reason? That it's crashing? Or let me just add a breakpoint here. Is something wrong with the breakpoint? What's the debugger output? Debugger. How do I get the debugger output? Don't even know. Why is my program not debugging? Let's put it in here. Okay. Yeah, it goes through all of them. That's good. And then our array is very big at some point. A bunch of numbers. And then in here, I say, okay, so we have our memory. In here, let's add a breaking point here. So our accumulator is that number, it adds up with the values. And then it finds undefined as well. What is, let's just debug this. What's a number plus undefined? Not a number. Maybe that's our bug. No. Because value is undefined. Wait, how does memory look like? This no, I can't see it. No, that's not the bug we verified before. So our accumulator seems to increase here, and we're 1,000 million billion. We're kind of reaching 1 trillion. And what's the end result here? 1,000 million billion 12 trillion. 12 trillion. Yeah, the big int didn't make any difference. So no, it's not that. I wonder what's wrong. Why is the number so high? Maybe one of the masks is not applied properly. Different. I wonder. We have our decimal number here. So what is it that we're doing? We're grabbing the memory address, and that's a number. Yep, and then we have the value, and we cast that from string to a number, then to a big integer. And then we kind of like transform the mask twice. First in this way, we parse it to an integer, and then we say it's a big int, and then we do the same for the second one. We parse it into an integer and then into a big int, and then we're using the big ints to do the bitwise operators, so it doesn't get truncated at 32 bits. And then we have our masked value, which is gonna be a big int, and now we downcast it to a number. Maybe that's where it's going wrong. What's I mean, could be. No, it shouldn't, because the masked value is never gonna be a crazy amount. No, so it's safe to downcast it, I think, and then we add it to the memory address. Memory address. Yeah, it's a tricky one, folks. 2 hours and a half into the stream, still doing the first part. I seem to have a solution, but there's a bug somewhere that I can't seem to find, and I hope it's not something silly that I'm spending so much time to solve. And if it is something silly, I hope to see it soon. We get the right answer for a different input. For this example input, we get the right answer, which is 165. But our own input, it doesn't work with our own input for some reason. I wish they provided more examples so I can test with. But I only have this one to work with in my own input, which is large. I know that I'm updating the mask every time I'm doing this. Let me read again. The puzzle instructions. The init program can either update the bit mask or write a value to memory. So yeah, here it's updating the bit mask every time. So that's what we're doing here. Can either update or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. That's interesting. So both this and this is a 36-bit unsigned integer. Wait, how? Oh, I think I see what's wrong. Let's try and get a visual representation of what a 36-bit unsigned integer looks like. Wikipedia. Bits. Oh, there's a lot of bits. Okay, so decimal digits. So a 32 integer has up to 10 decimal digits. And we definitely have some numbers that are higher than this is 9 digits, this is 8, this is 9 digits. Do we have some numbers in here that are more than 10 digits? Because that should be our bug. No, these are all seem to cap at 9. So it seems yeah, they're all 9 digits. Because if they're 9 digits, then it fits into a 32-bit integer. Value and memory addresses are both 36-bit unsigned integers. For example, ignoring bit masks for a moment, a line like mem811 would write the value 11 to memory address 8. I don't think it matters in our case because none of the addresses or values exceed more than, I'm not sure, because this is, yeah, this is a decimal. It doesn't matter. This is a decimal. But it's a 36-bit integer. Which we are doing here with big int. Number value. Yeah, we're already doing that. I think that's fine. Okay. Let's read on. The bit mask is always given as a string of 36 bits, written with the most significant bit on the left and the least significant bit on the right. The current bit mask is applied to values immediately before they are written to memory. So that's what we're doing here. We're applying the mask and then we're writing it to memory, to the value. The current bit mask, okay, so a 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. For example, so we already checked that, we're doing it right. Consider the following program. Yep. This program starts by specifying a bit mask. The mask it specifies will overwrite 2 bits in every written value. This one. The 2-bit overwritten with 0 and the 64th bit is overwritten with 1, which is what we're doing in our mask here with this trick, which we verified here it's correct. Maybe try a bigger number. Let's try a bigger number. Let's try this bit number. What happens here? So we have the OR bitwise. Okay, so let's look at the result. Wait, oh, we can get rid of this. Let's look at the result. So this is our number, this is our mask, and this is the end result. So we leave these two untouched. 1 and 1, that's good. And then 1 1 0 0 1, and then this is untouched, which is should be a 0, no? Because oh no, wait, which element is this? 1 2 3 4 5 6 7 8 9 10 11 12, the 12th bit. 1 2 3 4 8 9 10 11 12, 12th bit is 1. Okay, so that's 1. And then 1 0 1 1 0 0, so this is all a mirror. And then this one, I think this is out of range for this one, so this is just 0, this is 0, this is 0. Looks good. The masking we're doing, I don't see a bug there. The program then attempts to write the value 11 to memory address 8 by expanding everything out to individual bits. The mask is applied as follows. This is our 11, and then we apply the mask. So here, X leaves it untouched, 0, yeah, X leaves everything untouched. So if it's out of bounds, then it's 0. And then every number kind of changes that bit, 1 and 0. So that's the case here. For here, for every number that we have, it's kind of like copied over 1 0 0 1. Everything mirrors correctly, and then the x's are taken over from the original input. So here it's 11, here it's 1, and here we're out of bounds because this is I'm sure we're out of bounds, but let me just check. 1 2 3 4 5 6. count 30 bits here in this number. So here we are at 27 bits. So 30, 29, 28, 27. So that's 0. So this is not out of bounds. But this one is out of bounds, which is 0. But 0. So that's correct. Yeah, the masking is good. We mask it here. So this number is masked. That number doesn't mask it now. So what's the bug? Are we gonna find it? Or are we not gonna find it? This number is too large. We need a smaller number. Yeah, this is tough. This is tricky. I could try a different approach and just manipulate the strings. Instead of being clever with the or and and operator, I could just I could represent this in a binary string, and then I have this string, and I could just manipulate the strings to get a new binary, and then convert that into a number. That could work. Because I can't find a bug of what's going on here right now. We could try and do that quickly. So let's say, so instead of this, let's comment this out. And then, well, I need the memory address, so let's keep this. But what we're gonna do is instead is we have our mask, and let's split it, and then we're gonna map it bit, and then if bit is not equal to, if bit is equal to x, then remove whatever, otherwise remove bit. And that whatever is gonna be, if bit is equal to x, we need to take over the copy the bit from our original number. So let's say const new, not masked value, and then it's gonna be a large number. Let's say it's a big int. Oh, let's okay. So we're gonna need the const value binary, and then let's just say value binary is, what's the binary? I think parse, no, it's value to string to, okay, this is how we convert a decimal to binary. So it's gonna be value binary, it's gonna be a string, is it? Yeah, it's a string. That's good. And then we say it's equal to, so we need the index here. It's going to be equal to value binary at that index. But then we also need to take into account that we might be out of bounds. So let's do this in a new line. I'm going to wrap this in curly braces and do it like this, because it's going to be a bit long. So if bit does not equal to x and value binary is out of bounds and there's no value binary, then just return bit, otherwise return value binary at that index. I think that's kind of like what we want here. And then we have our masked value binary, and then we need to say const masked value decimal, and that's just gonna be parse int, or no, that ain't gonna be that, because we have a 36-bit binary now. So how do we turn that into, we need big int, don't we? Or wait, maybe that here's our bug all along, because what happens if we try to, yeah, that might have been our bug in the first place. What we are trying to do here is we're in here, we have our a 36-bit binary, and we try to parse that into a number and then into a string, and then I think that's what goes wrong, because not sure, because if it's going to be a 36-bit binary and JavaScript can only deal with 32-bit binaries, then what happens if you try to convert that to a number? No, I think it's fine. I think it's fine. Parse int masked value binary. Okay, and then we need to store that into memory address masked value decimal. All right, let's see what happens now. Let's see what happens now. What answer do we get? We get an error first. Mask is not defined, of course, because we're dealing with bit mask. Not a number. Maybe that comes from here. So if we say value, accumulator plus value, otherwise accumulator, maybe the number is here. I get 96. That can't be right. Okay, memory address, that's correct. Value binary is the value to string, and then masked value binary is the bit mask split into individual, and then mapped every bit is if it's not X, wait, or if bit is not X, or yeah, I think that's what we're looking for. 205, still way too low number if you ask me. So if bit is not X, then it's true, then return bit. Or if we are out of bounds of our value binary, then also return bit. No, then return 0. Okay, so else if bit is not equal to 0 to X, then return bit. And if there's no value at that point, then return 0, and otherwise return that. I think that's what we want. That doesn't change anything. Return bit. Wait a second. If value, let's do it like this. If bit equals to X, return value binary or 0, otherwise return bit. This is easier to understand. Still the same. I'm just gonna guess. I think this number is way too low, but I don't know, it might be the right answer. No. So what if bit is equals to x? So we're going over our mask using the let's use the debugger to see what's going on here. I'm gonna add a breakpoint in here. Wait, in here and here. Okay. So we have with our first variable. Should we use the example input? That's easier. What do we get for the example input? 1. Okay, so that's our bug. We have a bug there. Split to the right. Here. Oh, well, let's put that in here. Okay. So read debugger. So we have our, oh, wait. Why isn't it working? Okay, so our value is value binary is this, total value is to string. Our value should be a number. Maybe this works. Okay, right, so that was a problem. Value was a string, therefore string to string 2 would just return the same thing. We need to typecast to a number first. Let's run our own code again. Still we get 1. Okay, so something else. This is our binary, and then our bit mask is, what's our mask? Why don't we get the output of is this out too much in outer scope? Perhaps. I'm gonna add a breaking point here. So our bit mask is that's good. Our memory is empty. Our value is 11. Our variable is mem8. Our memory address is 8. That's good. The value in binary, so this is 11 in binary. And then we go over. So we are at the first bit, index 0. All right. Oh, I see what's wrong. We're using, yeah, we need to pad this with zeros. I think that's better. So value binary. How do you pad something in JavaScript? Left pad, I think. Left pad is a thing. In JavaScript, string. Here it is. Is it pad left? Pad. No, trim end. Pad start. Pass the current string with another string multiple times if needed until the resulting string reaches the given length. Pad start, pad with that with that length. Okay, let's do that. So we have our string here, and then we say pad start. We need to reach 36. A string with 36 length and pad it with zeros. All right, let's run it again. There we go. So we have our padded binary, and let's run it again. Now we get 0. Okay, so still haven't fixed the bug. Get in here. So bit index 0. If bit is equal to 0, so we don't need this anymore because it's never gonna be out of bounds. So get the value, return the value at that index. So value binary index 0. It's gonna start from left. Yep. Otherwise return bit. Okay, so let's add a breakpoint here. Get rid of these ones. What's our masked value? It's this. Oh wait, we need to, yeah, we need to join this first. Wait, let's do that at the top here. Map, and then we do a join, just like that. Yeah, let's run it again. So now we have a okay, now we have the binary and then the decimal. Good, let's run again. 165, we get the correct answer for the example. Let's try it with our input. Did this fix our bug from this number looks familiar, 904, but it's a bit different than our answer. This might be the solution. Let's give it a spin. Yes! 2.5 hours in for the first part. This took us way too long. I should have done this in the beginning. It took me 10 minutes to come up with the solution. Instead of trying to be clever with the bitwise and big ints and whatnot. I'm gonna leave this here anyway, but I'm gonna say this doesn't work for some reason. And then we can just move on. We can just move on to the second part. Yeah, so instead of using bitwise operator, we're just modifying the string, which is much easier. Oh, I should have done this from the beginning, from the start. Okay, let's refactor this into a bit shorter. If bit is that, return value binary index, otherwise return bit. Okay, and then we can actually make this a one-liner too. Great, still same answer. Split, map, join. Okay, good. Let's move on to part 2. This stream is already getting quite long. Second part. For some reason, the Seaport's computer system still can't communicate with your Fairies docking program. It must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder, which leads us to a YouTube video. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. So instead of modifying the value, we are modifying the address instead this time. So the following way: if the bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, the corresponding memory address bit is overwritten with 1. If the bit mask bit is X, the corresponding memory address bit is floating. Oh, this is tricky. Floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. Oh, I see. For example, consider the following program: mask memory 42 100 mask memory 26 1. When this program goes to write to memory address 42, it first applies the bit mask. So 42 in binary, this is the mask. Then we end up with, what do we end up with? The ones are ones, the zeros are, so vector rules. If bit mask bit is 0, the memory is unchanged. So if it's 0, it's unchanged. So these are copied over, 1 and 0. If it's 1, then it's overwritten with 1. So these are 1s, all right. And then XX. After applying the mask, 4 bits are overwritten, 3 of which are different and 2 of which are floating. And these floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. Oh, I see. So if you're gonna have 2 to the power of number of x's It's going to be the amount of possibilities, which can be really long, because some of our inputs have, some of our masks have like 5 or 4 bits excess, which gives us a lot of possibilities. So next, the program is about to write to memory address 26 with a different bit mask. So memory addresses, these memory addresses are written, 100 is written to this memory address, and then 1 is written to all of these. So the entire 36-bit address space still begins initialized to the value 0 at every address, and you still need the sum of all values left in memory at the end of the program. In this example, the sum is 208. 208. Because, why is it 208? Because we write this value 4 times, should be 400. Okay. This results in address with 3 floating bits, causing rise to 8 memory addresses. So we write 1 to 8 different addresses, because that's what this bit mask gives. So then we have 8 times 1, so that's 8. But then we write 100, we write it to 4 addresses. Oh wait, oh I see. Address 26 is being replaced here with 1. I see, and 27 as well. So we're left over with 58 and 59. So that's 200, and then the 8. Okay, that makes sense. All right. So going back to our inputs, example input, we don't get an example input. Yeah, different example input this time. So we need to, let me think. Our mask is this one, and then I'm gonna try and figure out if something I can come up with quickly, or if it's too challenging, then I'll have to cut the stream short and solve it off stream, and then recap my solution tomorrow for tomorrow's stream, because I don't want this to drag on for hours. We're already 3 hours in, and so let me think. We have the mask in here, so now we're masking the memory addresses instead of the values, and the memory address is, so first we need to turn this address into a binary representation, and then we apply the mask according to these rules, which is 0 leaves it unchanged. So when it's 0, we just copy over. Let's kind of like reuse part of this code here. I need this in the second part too, so I'm gonna leave it here. Move to the top, and then we have our memory and our bit mask. I'm gonna wrap this in a immediately executing function, so we don't get variable name collisions. Just gonna basically say create a special scope for the first part, and then let's do that for the second part as well. Okay, and then let's copy some of this in here, and let me move this a bit to the right. And then we have so we still have the same code. We need to update the bit mask, so that's still the same, but now we get the memory address and we have the value. So instead of changing the value, we need to change the memory address. So we can say memory address binary, which is this to binary, and then we pad it, so that's good. And then mask the value binary, we look at the bit mask, and then let's say masked address memory address binary, and then we use the memory address binary here. Then we say split the bit mask, and then if bit mask equals to 0, we leave it unchanged. Let me write this down in more than one lines, because we're gonna have a bit more complicated logic for this one. If bit is equals to 0 in our mask, then we just copy over what's in the original one. If bit is 1, then we return 1. Else if bit equals to 1, then we return 1. And otherwise it's going to be x, so return x. Well, return bit, yeah. And here bit is equal to 1, we also return bit. So we can just say this, and then here we can say if bit equals to 0, return memory index address, otherwise return bits, and that's going to be either 1 or x. Okay, so we can write it shorthand as well. And then the masked memory address binary. So we have the binary, which is going to be x's. So now we need to calculate all the possible different memory addresses, given that we replace x. That's going to be interesting. That's going to be interesting. We kind of like need to have a loop here. We need to have a loop in here that for each x, it's going to be nested loops too. I wonder what's the best way. Maybe this time around we do need to have need to use the bitwise operator, because if we're going to take the string manipulation approach, we're going to have, for the first bit mask, we have 1, 2, 3, 4, 5, 6 x's. So we need to, for each x, there's 6 to the power, or 2 to the power of 6 possibilities, which is 6 nested loops basically. 2 to the power of, well, what is it? This 6, 64 different memories, because yeah, x can either be 1 or 0. So I could replace all x's with 1 and then all x's with 0. Then we get 2 possibilities at least. But then I need to like if this is 0, then get all the possibilities for those and so forth. Oh, So this code is correct. This is kind of like, but we need to go through the masked memory address binary and then compute all the possible decimal combinations. Yeah. I wonder how can we do that. I could use a while loop while this is tricky. Trying to think how I'm gonna compute. So what's our, let's use the example input here. Well, this has a lot of possibilities. That's why we're not using this example input. Yeah, this one has a bunch of x's, so no, let's use our own input. And then I added a breakpoint in here. I added a breakpoint in here, so let's go until that point. And so this is our masked memory that we need to work with. And we need to go through every x. I mean, I could split it and I could filter out the x's and their indices. And then I could say for each x, go through all the other x's and then manipulate it like that. So this value, can I somehow copy this value? Local, yeah. Let's copy this value here in our playground. And so we have our value here. And what are all the possible values? I mean, it can be like this is a possibility if this is 1 or 0, and then everything else is 1 or 0. So there's like 64 different combinations. We need to find all of them. How do I do that? Well, if I could just go through, this is a string, and I need to find out 64 possible strings where x is. This is really challenging. I can split this into an array and grab the x's out and their position, and then I can loop through that new data through each x. Yeah, this is going to take me longer than I had hoped for the second part. to find out the different all the possibilities to write to the memory, because that's the only thing we need. Otherwise we have everything in place in here. We just need to have these two inside a loop where we write the value to all the different memories that we compute, and then we sum it up, and then we have the answer for part 2. So we're not that far off. We just need to find a way to compute all the possibilities for this string. So replace the first rightmost x with 0 and 1, but then all the other x's are 1 or 0. This is, yeah, or we can say they're 0 and then 1 or 0, and then they're, yeah, this is tough. So I'm gonna cut the stream short here. I'm gonna have lunch, and then I'm gonna come back to it later, and I will explain how I came up with this the solution for this part tomorrow morning for the 15th day. Thank you for watching so far. Appreciate you sticking around. I'm going to, well, I can just say I'm going to commit this code to the repository, and well, I'll commit the code for both solutions later on today, but you can you'll be able to find my solution here in this repository. So keep an eye out on that. I'm gonna push the solution for both parts later on today. After lunch I'm gonna do it, and then yeah, thank you for sticking around. If you want to get in touch with me on Twitter, I'm _maximization. Let me paste my profile in the chat as well. Get in touch with me on Twitter, and then if you want to discuss advent of code, today's problem, or a solution, please, yeah, my DMs are open. I'm curious. Let's chat. And yeah, thanks for sticking around for this long. I'm gonna continue off stream after lunch. I'm gonna post the solution in the repository, and I'll see you tomorrow. Tomorrow I'm gonna go over the solution before we go on to day 15. Tomorrow I'm gonna stream at the same time, 10 a.m. Central European time. So I hope to see you then. Thank you for watching, and see you tomorrow. Bye bye.